So this lecture is going to put everything we've done so far with electrostatics, forces, and charged objects together. Let's start off by looking at an atom. Element number 6 on the periodic table is carbon. It tells me here, I know that the periodic table tells me carbon is the name, 6 is the atomic number, C is the symbol, and 12.0107 is the atomic mass. In order to find the number of neutrons here, I take the atomic mass of round it to 12, minus 6 is the atomic number, tells me it has 6 neutrons. Because it has valence or shell electrons that are not full in its valence shell, it does not have 8. It wants to have 8 because it's spilled into the second orbital. So it's going to react in order to satisfy the electron rule. When the electrons in the valence shell have satisfied the rule, they're stable. But carbon is not. Carbon is very reactive. In this case, we can apply the concept of atomic theory, is that all matter is composed of atoms. All matter isn't composed necessarily of carbon, but carbon is a building block of, say, living organisms. So if we look at an isotope is simply an atom that contains a variation in the number of neutrons in its nucleus. So carbon-12 is the most common and very stable form of carbon, is pictured above right. Here we go. But carbon has C12 has two isotopes, carbon-13 and carbon-14. It simply has 7 neutrons in carbon-13 and 8 neutrons in carbon-14. They're just variations of the same atom. They still have 6 protons and 6 electrons, but they have a different number of neutrons in the nucleus. Those are isotopes. If we talk about the basics of electric charges and forces, we need to realize that like charges will repel and opposites will attract. That charge is simply a fundamental property of matter. They can be only negative or positive, and they can repel or attract based on the charges themselves. That even the tiniest imbalance of charge can lead to static electricity, such as scuffing your feet on the carpet and touching something metallic. So this zap that we get is really just a transfer of your net surplus of electrons. And lightning is just a larger scale. Instead of rubbing your feet, we have clouds that, let's just say, charged by friction, and then ice and or water droplets separate the charges in a cloud. And we see the same zap on a larger scale as lightning. Lightning is a form of electrostatics, like that of zapping a door handle after rubbing your feet. So back to the basics. Like charges repel, opposites attract. Coulomb's law here applies that very concept. That if I look at what Q1 and Q2 are, these are simply the charges of particles. At some distance, they can apply a force, or exert a force on another object. We know like charges repel, right? Pluses or minuses, and then opposites will attract. D is the distance. The distance is very important. The relationship of distance to electric force is an inverse square, much more significant than just the direct relationship of either one charge. When we look at the units of measurement, the electric force is measured in newtons. The unit of measurement for charges are in coulombs. So Q1 is going to have a charge in coulombs, Q2 is going to have a charge measured in coulombs. And the distance can be measured in meters. When we get objects very close together, we are increasing the electric force between the two objects. So now we'll move into charging by friction. There are 2 ways that charge can be transferred, by friction and by contact. When we scuff our feet or shoes on carpet, we feel the tingle and hear the zap when we touch a doorknob. This is electrostatics, and here's the person walking here and they gain a net charge. If I rub 2 objects that are neutral together, one of them can gain electrons and one can lose electrons. It's simply just saying that 2 different objects can have an ability to transfer charge. Electrons are what are being transferred by friction, or rubbing the materials together. One object gains electrons as the other loses electrons. And this is your principle, or the conservation of charge concept. Looking at the triboelectric series, by rubbing 2 objects together via friction, we can observe the transfer of electrons, not by seeing them move, but by seeing how objects around them behave. If an object moves, we can infer that an electric force was exerted on them. Some materials are more willing to give or receive electrons than other materials. The positive side, these are the ones that are willing to give. They simply just have the structure of the material was willing to give up the electrons. And objects on the negative side, these are the receivers of those electrons. So if you use this table here, you can pause this and just determine what's going to happen in terms of gaining or losing electrons. A rubber balloon against cotton, a rubber balloon against wool, a copper pipe against your skin, and a plastic ruler against rabbit fur. So here we can talk electrostatics and polarization. Polarization is where opposite charges attract and like charges repel. That we know this principle is taking place here. simply by placing a charged balloon near a neutral surface. The balloon was charged by friction. The electrons in the balloon are going to repel electrons in the wall. We see this by applying Coulomb's law. The new surface has a slightly positive charge, not a net charge, it's just relocated these electrons. So the negatively charged balloon is going to be attracted to the positively charged wall. Electrostatics is all about forces generated by unmoving charge. So a negatively charged balloon can stick to a neutrally charged wall due to these electrostatic forces. So when we look at the pop can race, why did the can move? Well, the charged balloon applied an electric force to the can because it was charged. Here we can see the balloon. The balloon had to be charged. That's key here. It was charged by friction. Placing the balloon near the can polarized the atoms in the aluminum, thus repelling the electrons, not outside of the can. They're still inside the can, but I'm showing you for visual appeal. Therefore, the positively charged surface was moved or attracted to the balloon. So it moved towards the balloon as we moved down the hallway. This is a direct application of Coulomb's law. So let's talk about the process of grounding. It's simply the removal of a net charge. When you rub your feet on the carpet and you gain a net charge, you do not maintain this charge forever. Instead, once you touch an object, you hear that zip or that zap. You just ground it out by neutralizing your net charge to zero. Grounding removes any excess charge leading to a neutral charge. So we can charge objects by contact. Electrons can be transferred from one material to another simply by touching, and sometimes this is called conduction. This is what we call charging by contact. A neutrally charged object can gain charge when it comes into contact with the charged object and electrons are transferred. Sometimes you can actually transfer without actually having to touch it, and we saw that with our aluminum foil in the balloon. Let's compare conductors to insulators. Conductors allow for charge to flow through it, whereas insulators do not allow for charges to easily flow through it. So we had this, let's just say we have the scenario with this conductor here, this aluminum head. It looks like kind of an alien here. That a metal sphere is mounted on an insulating stand, touched by a charged plastic tube. Well, the metal sphere then acquires a negative charge located at the point of contact. But since the metal is a conductor, the charge quickly distributes itself across the surface of the sphere. So all of these electrons, they're not going to stay next to each other because they're repelling each other. So they're going to be equally distributed. This is a conductor. It allows for that. Whereas an insulator does not allow for electrons to freely move. Wool, wood, and rubber are good insulators. If we look at what a wire is a metal, a good conductor of electricity, surrounded by an insulator. Right? Wires are conductive metals surrounded by the rubber insulation. We'll talk more about this when we move into electricity. Remember, electrostatics is unmoving charge. Electricity is actually moving charge. Let's talk electroscopes. Charges exert forces on objects. If I place a charged rod, right, negatively charged rod, near an electroscope, it's going to repel electrons down to the leaves, and we see the leaves separate. In this case, we would have this is polarized. This is what we're looking at. It does not have a net charge. So we're simply saying that a negatively charged rod exerts electrostatic forces on the electrons within the electroscope. And this picture illustrates that very concept. We cannot see the electrons, but we can see the behavior of the objects responding to the electric forces as stated by Coulomb's law. Right? Negative charges will repel negative, and they would thus be attracted to the positive. But the electroscope has no net charge here. And in this case here, we can just say that all of the electrons and protons are equally distributed. We're seeing no movement. This we could say very confidently is neutral. When we look at charging by induction, so we have to look at a scenario here. So if a charged object is brought near a conducting surface, even without contact, electrons move in the conducting surface. So here we have two metallic spheres, A and B. Letter B, we place a negatively charged rod next to them. And that's key, because it's going to repel the electrons, right? Here we see charge polarization. The atoms in the sphere don't move, only the electrons do. And what happens is, I can separate these metallic spheres A and B, and this is still located here. So technically, there's still a force that's being exerted here. But B had gained the excess of electrons that were repelled, right? These are conductors, so they're touching, so we can transfer electrons from A into B. And then by the time I separate them, letter D here is very obvious. B has been charged by induction, and so has A. A has lost electrons. This charge has been induced to it. So it has a net positive charge, whereas B has a net negative charge. This is where the electrons that came from A went. So we can see conservation of charge. 6 electrons went to B, that's got a net positive of +6 charge. And last but never least, the Van de Graaff generator. The Van de Graaff generator is designed to have the aluminum head gain a net positive charge. This electric charge generates an electric force on objects around it. It can attract a piece of aluminum foil by polarizing it. Right? We saw the attracting of electrons to the aluminum. Right? It's polarizing it. So therefore, the electrons want to jump to it. It can hold on to a negatively charged balloon, and it can zap people surrounding it as it takes electrons from us. We feel the transfer of electrons as shock.